Okay, we saw earlier how you can solve a system of linear equations by simply, or actually I shouldn't even have said linear equations, you can solve a system of equations by just seeing where the two graphs intersect, and that point that lies on both curves makes both equations true and is therefore a solution to the system. Okay, so we're going to do this now ourselves, graphing things by hand, and we'll get the same results, making sure we can just do it without our calculator. So let me put up some equations. Okay, so there's my two equations. They make a system of equations together. If I want the x and y combination that makes both of these true, I'm going to find this by graphing. I need to be able to graph them. I think I'll just put them in y equal form rather than doing intercepts, so let me do that. Okay, because put both of these equations into y equal mx plus b form. Now I'm just going to go ahead and graph both of these. I'll graph the blue line. It has a y-intercept for a starting point at 1. Okay, this is going to get a little hard. I don't have a stylus today, so hope I can do this pretty well. After my starting point of 1, I'm going to go up 2 over 1. Okay, and I'm going to keep doing that. Up 2 over 1. Maybe I'll go down 2 and over left 1 to get some more points on the other side. And then I'll draw the line between those. And it's important when you're graphing these systems that you do have graph paper, because we are going to be finding solutions, so it has to be pretty accurate. So now let's graph the red one. My y-intercept is 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm way down here. I can't go down 5 over 2, so let me go up 5 and left 2. 1, 2, 3, 4, 5, and left 2. Oh, look at that. I've already found my intersection. But I'm going to keep going. 1, 2, 3, 4, 5, 1, 2. Another point. Let me draw the line. And nicey nice, look at that. I have a point of intersection right here. Okay, and I'm just going to read that from my graph. Okay, that location is left 2 from the origin, so minus 2 for x. It's down 3, negative 3 for y. And negative 2, comma negative 3 will be my solution. If I put that into both of these original equations, they would both come out to be true statements. Okay, so that's the solution by graphing. Okay, try this one, guys, and we'll go over the solution on the next page. We'll check first to make sure we have the same thing. If you do, you can skip the explanation, but then go on. Okay, I want you to... Oh, wait, hold on. Ugh, this one is a little difficult to graph. When you're graphing the black line, it's going to be tricky, okay, but we can do this. This point right here, look at that, I found the arrow. That's 5/3, okay, it's almost 2. From that point, I just keep going down 1, okay, so there's down 1, down 2, see how I'm always a little below the line, down 3, down 4, down 5. Okay, then I can go over my 3 spaces. So I'm about there. Okay? On there. Maybe a little higher. Okay, so that's about starting at 5/3, then down 5 whole steps and over 3 whole steps. And I did that again, and I made an estimate. So of course this is a very rough estimate. And I think I came out to be about -4, -5. But I'm going to go ahead and test this and see if that's right. So let me test that. Can I say -5 is equal to, negative, a negative 4 minus 9. Ooh, that one works. Let's see if we got lucky with the other one. Is y, negative 5, equal to 5/3 times, for x we had negative 4 plus 5/3. That's going to take a little calculating. So this is negative 20/3 plus 5/3 is minus 17/3, which, so I'm a little off. Okay, so this minus 5 is more like, 15/3 if you want to compare. So I'm close, but not quite close enough. Alright, but as good as I could get by graphing. I want to take a minute and stop and think about the different types of solutions you can get when you have two equations, two linear equations. What normally happens, what happened in our last examples is we had one line, we had a second line, they intersected in one single point. So, that's what we would call a consistent and independent. Set of equations, okay? There is one solution. The graphs intersect. Okay? But other things can happen as well. So let's see what happens in other situations. Let's say you had this system of equations and you took the time and you went ahead and graphed it and you found the first solution, maybe a black line. Okay, it gives you something that looks like this. And then you carefully figure out the second solution and you carefully graph it and you say, whoa, what's going on here? I've just graphed the exact same line. That's consistent and dependent. Okay, there are an infinite number of solutions. Okay, because every point along this line, all right, is going to make both of those equations true because they're the same line. Okay, how can you recognize that they're the same line? It's pretty simple. If you reduce this one by 2, 2x minus 5y is equal to minus 10, and then multiply everything by negative. You look at that and say, of course, they're even the same equation. That's why they're graphing the same line. So you have an infinite number of solutions. So how do you give this solution? You could say x is equal to any number at all. Okay, because as you can see, the domain of that line, all real numbers. But y depends on x. Okay, it is a dependent variable. So you would have to say y is equal to, and here's where I would take this equation and solve for y. So let me just go the in-between. 5y is equal to 2x plus 10. So I can go over here now. Y is equal to 2/5 x plus 2. And this would be my solution. Y is dependent on x, although there is an infinite number of solutions, because they are the same line. Alright, let's try one other possibility. In this system, we have two equations, and they are different equations, as you can see, but when you graph them, you're going to notice that, yeah, the y-intercepts are different, but the slopes are the same. Okay, so here could be one line, but the second line, maybe that was this one about, but the second line, that one is just parallel. Okay, so you have these parallel lines. Will they ever intersect and get that solution that makes both equations true at the point of intersection? No, parallel lines never intersect. So here there is no solution. This is an inconsistent solution because there is, or inconsistent system because there is no solution. Alright, let's try one more thing. Alright, we want to be able to solve these systems of equations algebraically. As you could see with graphing, we were just getting estimates, limited by how well we could graph. So if we do it algebraically, we'll get the exact answer. So there are two methods the first method, and this is a nice method because it will have nice extension into other types of equations, not just linear, is substitution. And you want to be looking for a variable you can solve for. And in this case, when I look at this, I say, oh, it would be pretty easy to solve for this y in the second equation because it already doesn't have a coefficient. So that's what I'm going to do. So I'm going to take this and say y is equal to 7 minus 2x. Okay, so now I have the a y is equal to, I've solved for y, and I'm going to take this expression for y and put it into the first equation instead of y itself. So this first equation becomes 5x minus 3 times, always use your parentheses when making substitutions, 7 minus 2x is equal to 23, and of course I can solve that fairly straightforward. And 11x is equal to 44. Look at that, x is equal to 4. That's a nice number. It's really nice thing about this method is it's quite easy to find y at this point, because we'll just go back to this equation. I know what x is, 4, so y is 7 minus 2 times that value, 4 for x. So 7 minus 8 is negative 1, y is equal to negative 1. Now remember, the solution to a system of equations is a point. We're going to give the ordered pair 4 comma minus 1. So your solution must be in that ordered pair. All right, I'm going to give you one to try by yourself using method of substitution. All right, give this one a try. I'm going to come back in a minute after you've paused it, and we'll see if we agree. All right, I got a solution negative 3 comma negative 2. Great, if you got that, we got that last method to go on the next slide. Otherwise, I'll run through it really quick. When I looked at this, I decided that the x would be the easiest thing to solve for, okay? And make the substitution when I get that. So I'll go ahead and solve for x. In the first equation, x is equal to 11 plus 7y. Once I have that, then I go and put it in to the other equation, this time the second equation, wherever x was. So 5 times parentheses 11 plus 7y plus 4y. And go ahead, solve all that, you get y is equal to negative 2. Once I have y is equal to negative 2, it's a matter of going back up to that equation I had for x and figuring out what x could be based on now that I know what y is. And then put them in an ordered pair for an answer. Alright, let's try elimination next. Okay, one of the things you want to be able to do is look at a system of equations and know which is the better way to solve them. When I looked at this equation here, or this system of equations, because they used to go together, I said, wow, I don't really have anything without a coefficient. It's going to be a little bit of extra trouble solving for x or y. But look what happens here. These coefficients of x have the same number. They're both 2, and one is even positive and one is even negative. So life couldn't get any better for us if we happen to add these two equations together. I am perfectly within my rights to do this, okay? I'm adding two equivalent things. Okay, it's like adding the same thing to the left and to the right. It's just that they look a little different. But I'm allowed to add these two equations together. When I add the x terms together on the left, I get 0x, so you don't even need to write it. If I add the y terms together, it's minus 3y. Adding the right-hand side of the equation together, what do I get? 6. So basically I get y is equal to negative 2, and I've eliminated the x variable, okay? That's the whole reason for doing this. But now that y is a negative 2, I have to go back and find x. So go back to either one of your equations, doesn't matter which one. I'll go back to the first one because it's got a positive first. 2x minus 9 times y, which is now a negative 2, is equal to 34. Let me just figure this out real quick. Plus 18. X is equal to 8. So together, my solution, 8 comma negative 2, solves. Both of those equations will come true. Okay, I want you to try this problem. If you know what the trick is, that's great. Go ahead and do it. If you want a little hint, the idea here is, substitution is not a great idea because you don't easily solve for A or B. But elimination isn't perfect either because they don't have the same coefficient anywhere. So what you have to do is you have to make them have the same coefficient. Kind of do a little coercion here. So we're going to take this first equation times 2, and we'll take the second equation times 3. So what I was doing is I'm trying to eliminate this b variable, and basically it's kind of like a common denominator. So now it's going to be a common coefficient. Okay? So try that, rewrite both of those equations, and then use elimination. Okay, I got a solution -1, 1. You could put those in and check and see, and indeed they both make that one solution, the x and y pair, makes each of those equations come true. So hopefully that all worked out for you, and I'll see you in class.